I'm very glad to introduce you Fred Walter as our seminar speaker today. Fred is a professor in the physics and astronomy department of Stony Brook University. He got his bachelor degree from MIT in physics and PhD degree in astrophysics from UC Berkeley. He came to Stony Brook in '89. He is an observational astronomer. He has one of the best jobs in the world. He observes exotic objects in the universe. He uses, say, different types of telescopes to study galactic novae, brown dwarfs, sun-like stars, etc. Today he is going to talk about the sun, which is the source of virtually all processes in the atmosphere and in the oceans. In addition to be an outstanding scientist, Fred is known to almost all the faculty as the president of the university senate. He devoted lots of time and energy, selflessly, tirelessly, to maintain the integrity of the university and to improve the quality of the university. So we owe him a great debt for his service. Today, we are really honored to have him as our seminar speaker, so let's welcome.
Well, thank you for that very kind and somewhat exaggerated introduction. Now, I've been here at Stony Brook for 25 years, and I believe this is the first time I have been to Endeavor Hall. It's really a pity, you know, the university gets too compartmentalized at times, and I know that some of you are doing really good work on terrestrial climates, and I'm interested in the sun. I study stars like the sun, and there's quite a bit of overlap, or there should be, between our two interests. After all, the sun is important for driving the Earth's climate. That's where the energy comes from. And I am here today to tell you why you should be interested in the sun and to tell you something about the sun and maybe where the sun is going in the next few years. As a disclaimer, I do not do the terrestrial atmosphere, and I really don't do the sun. I do stars like the sun. The sun is too complicated. It's too close and we have too much information about it. So anyways, this is the sun in time. Why should you be interested in the sun, about the sun? Well, I'm going to concentrate on solar magnetic activity. And where's the button for this? Okay. In the year 1610, Galileo pointed his telescope at the sun. Do not do this yourself. He did not know any better, but he discovered sunspots. This is a drawing that he made and published in 1613, but he observed sunspots in the year 1610. We know that shortly after Galileo started studying spots, they disappeared. Spots went away. This is a time known as the Aunder minimum, name given by Jack Eddy in the 1970s. This plot shows in magenta the number of sunspot groups as a function of time from 1600 to 1800. And Galileo observed here, and a number of famous astronomers observed up to the year 1650 or so, and saw sunspots and sunspot groups. Groups are easier to see than individual sunspots, so we count groups as important too. And then the spots went away. And it's not because nobody observed, the spots seemed to go away. And then they came back about the year 1715, sunspot numbers, sunspot groups. The Wolf sunspot number is there's a formula you use. It depends on, it's the number of groups and the number of spots you can see above a certain size. It's complex. I'm not going to get into it. But the fact is that there is a lack of sunspots here, and it's not because people weren't observing. Hevelius drew this picture in 1644 showing a large sunspot group crossing the surface of the sun. At about the same time, between 1645 and 1715, there was an era called the Little Ice Age. Actually, this is the deepest part of the Little Ice Age, which lasted for a couple of hundred years, where temperatures in northern Europe were below average. We don't know what happened to the rest of the Earth because the record is sparse, if it exists at all. So all we can say is that during this time of few sunspots, it was cold in northern Europe. And the question that is on everybody's mind is this a coincidence? Or is there something causal here between sunspots and terrestrial climate, or at least temperatures in northern Europe? What's going on? Well, let me give you a lot of background here. We're going to start with the sun. This is what I do. I do stars, so I can tell you something, I hope, useful about the sun. The sun is a G2 star. G2 is a spectral type. Its effective temperature is about 5,780 Kelvin. A star is merely a self-gravitating ball of gas that is sufficiently massive that the interior temperature and pressure can support stable hydrogen fusion. These are the reactions that go on down here. You end up with 4 protons, give you a helium nucleus. Other than that, the sun is very, very simple. Actually, that is the simple part of the sun. I love this cartoon. We know a lot about the sun because it's close. We get a lot of light from it, a lot of photons. Here's a spectrum in visible light, and all those dark bands are different elements, mostly iron, from the sun. The sun has lots of parts that we have cataloged. Astronomers like to catalog things and do morphology. There's a core, which we don't see, and there's a radiative zone, a convection zone. The convection zone is the outer 30% of the sun by radius and about 2% by mass, but it filters everything coming from the interior. The outside, you've got coronal loops and spicules and faculae and all sorts of neat stuff. What's important about the sun is that it's not constant. It is a variable star. All stars are variable. We have yet to find a star that does not vary. If you look hard enough, everything changes. There are a number of timescales. On time scale of 10 to the 10th years, you have the nuclear revolution timescale. The sun runs out of fuel in 10 to the 10th years. It's about halfway through that process now. And clearly, you run out of fuel, the sun is going to change. It's going to become a red giant. There's a magnetic diffusion timescale for about 10 to the 9th years. This is the timescale for any primordial magnetic field in the radiative core to diffuse out and get lost. Well, we're well past that time. It's thought that there probably isn't much of a magnetic field in the core of the sun. 10 to the 5th years is the thermal diffusion timescale, the Kelvin-Helmholtz timescale. This is the time it takes the sun to radiate away its thermal energy in the convective envelope. That means that if the sun were to turn off today, you would not know for 10 to the 5th years. You would still get photons coming out of it for another 10 to the 5th to 10 to the 6th years. The time scale I'm going to be interested in later today is of order of a century or a few centuries. Causes are unknown. It's not clear why. There should be variations on these time scales, but there seem to be. On 11 or on 22-year time scales, you have the solar cycle. It's a 22-year magnetic cycle. The polarity flips every 11 years. The number of sunspots changes every 11 years. There's a 27-day rotation period. It's actually more like 30 days at the pole. The sun rotates differentially. It's a ball of gas. It's not a solid. And then on time scales of minutes, we have magnetic recombination, solar flares, coronal mass ejections on time scales of hours to days. So the sun varies on all time scales. Solar revolution. We're here. The sun has one solar mass, one solar luminosity, and its radius is one solar radius, all by definition. If you go into the past, the sun was fainter. Solar evolution, the nuclear revolution, is driven by pressure balance. 4 hydrogens, 4 protons are converted into 1 alpha particle. The pressure is given roughly by nkt. N is going down, therefore T must be going up. Because the mass of the sun is constant, you're in hydrostatic equilibrium. So the luminosity of the sun is increasing with time. The temperature is going up. Nuclear reactions proceed faster at higher temperatures. So the luminosity is going up. The consequence is that the sun is now 30% brighter than it was when the Earth was formed. The radius is somewhat larger, and the surface temperature is about the same. It's a little bit hotter than it was. And in the future, these trends are going to continue. I don't worry about these things because we're talking of billions of years here. In 5 billion years, the sun becomes a red giant. The most interesting thing about the sun in time is the faint young sun problem. Why is there liquid water on the Earth today when the sun 4.5 billion years ago was 70% its current luminosity? The equilibrium temperature on the Earth was about 200 Kelvin. Everything should have been frozen and should have stayed frozen. The solution, we think, is simple. The details still elude us, but the solution is simple. It's greenhouse gases. The atmosphere was different back then, and the temperature on the surface of the Earth has always been above freezing. I'm not going to talk about that any further because even though the sun in time, I deal with stellar evolution in young stars, that's not really germane to what most of you are interested in. Here's the 11-year cycle. This is the image of the sun in the light of helium-2, 304, the Lyman alpha line of helium-2, singly ionized helium. And over the magnetic cycle, you go from a sun that's fairly inactive or quiet. You just see the surface that's not doing much. And over time, you have these active regions forming. They form in bands at high latitude and low latitude, and they approach the equator as you go towards the end of the cycle, and then everything disappears. This is what the sun does every 11 years. These bright regions, they're called active regions, are regions of concentrated magnetic flux through the surface of the sun. In optical, these are sunspots. Here's the visible light, visible image of the sun, 2 images roughly 6 years apart, showing spots on the active sun and a lack of spots on the quiet sun. There's magnetic field everywhere in the sun, and we get confused. I get confused. A lot of people get confused when we talk about magnetic fields. The sun has an overall global field with a strength of order 1 to 10 Gauss. You can measure that in interplanetary space. You get far enough away from the sun, the dipole approximation holds, and you can estimate what this strength is. Or you can look at the pole and try to measure it precisely. You go to the sunspots and measure the magnetic fields. We're talking about 2 kilogauss fields. So the field gets concentrated in places. And if you look in between the spots, there are bright regions and dark regions. They don't show up well in a white light photograph, but they show up much better in these types of images. You see bright regions and dark regions. And the bright regions have higher magnetic flux, and the dark regions have lower magnetic flux. And there is heat channeled along the magnetic field lines. The bright regions are called faculae or plage, and the dark regions are the spots.
So, Fred, are you looking at one pole of a dipole, or what are you looking at when you see the spot? Is it?
You're seeing both poles. Spots come in pairs of 2 polarities. There's a north pole and a south pole, and depending on which half of the cycle you're in, the north pole leaves or the south pole leaves. But they're bipolar structures. So the surface of the sun is turbulent, it's convective. Granules have sizes typically about the size of the Earth, give or take. There's a 5-minute time scale. The whole sun is oscillating on a 5-minute time scale. And this is just what the granulation pattern looks like in part of the photosphere. And it's these motions of the gas that drag up the magnetic field. The magnetic field is strongest in these dark regions, the network, where the gas is coming. The gas actually, take that back. It's concentrated in these regions. The gas comes up in the middle of these granules. It's like watching a pot of water boiling on the stove. Start this up again. So the gas the upwelling is the center of the granules, and it goes back down, it cools off and goes back down in the darker networks, and the magnetic field is dragged along with the gas and concentrates along these networks. And if you take a look in the chromosphere, this is the photosphere. If you look at a higher level up in the atmosphere, the temperature increases going up. In the chromosphere, if you look at the light of calcium K, for example, at about 8,000 degrees, you will see sort of the opposite of this. You will see a bright pattern of networks with these dark granules in the middle. This is what drives the concentration of magnetic fields. The fields build up in these dark areas, and you end up with magnetic flux tubes forming. This is the chromosphere. This is the transition region. Technically, this is like iron 9 or iron 10. Temperatures are close to 1,000,000 Kelvin. The field emanates from the surface down here, and you can see the flux tube structure. These are 2 kilogauss fields at the surface, the North Pole here and the South Pole here, or vice versa. And you can see these are unresolved at the limit of our resolution. They're unresolved at about 100 kilometers spatial resolution. There is an awful lot of fine structure in the sun. You can see some of these in absorption in the foreground, emission here in the background. What causes flares are magnetic recombination events when you happen to have a field going this way running into a field going this way, and the field annihilates, and you dump all of that energy into the gas and heat it up explosively. So the spots, the sunspots, are these regions at the base of the loops where the magnetic field is concentrated. We can count sunspots. We couldn't count loops until the last couple of decades. You need satellites to do this, but you can count sunspots from your backyard. The Chinese have records of sunspots going back millennia. They didn't do systematic observations, but you can see large sunspot groups with the naked eye under appropriate conditions. I have seen them from Stony Brook. You look at the sun through a fog bank, be careful, but you can do it, and you can sometimes see large spot groups. So this is the record, and it's fairly regular. There's an 11-year period. You Fourier transform this, and the 11-year period comes out. The times between peaks of maxima vary from 8 years to 14 years.
How deep are these spots? Are they just surface, or do they go into the interior, or what do you see? And when you see a spot,
you always see down to one optical depth. One optical depth in the sunspot is depressed by a few hundred kilometers below the one optical depth in the photosphere. There's a pressure balance here. The reason that spots are dark is because the sum of the thermal pressure, NKT, and the magnetic pressure, V squared over A pi, is the same inside or outside the spots. The spots are cooler, and they are depressed. It's called the Evershed effect. You actually see this as the spot rotates off the limb. But given the size of the sun, it's a surface phenomenon. The sun is 700,000 kilometers in radius. We're talking 100 kilometers. That's nothing. So anyways, this is the record of sunspots from 1750 up to, a couple of years ago. And it's a fairly regular pattern. You can look in more detail at the magnetic cycle. If you plot the latitude at which the spots are as a function of time, you get this butterfly diagram. Spots emerge at high latitude. If you think 30 degrees is high latitude, flux actually emerges about 45 degrees. And the spots migrate towards the equator over the course of this 11-year cycle. Every cycle, the magnetic polarity reverses so that the North Pole will be north and south and north and south, and you have pairs of spots here. They always come in pairs, and there will be a north polarity and a south polarity spot, and one leads the other, and that will reverse 11 years later. Here's sunspot numbers, area of the hemisphere covered with spots, and it gets up to 0.5% or so. So the sun never turns black. We do have stars where 50% of the surface is spotted. The sun is not like that anymore. This is the very crude hand-waving figure of what happens to the solar magnetic field. You have to start somewhere, so you start with the colloidal field oriented, in this case, down Differential rotation winds the field up. You end up with a toroidal field. You concentrate the field as you stretch it out, and it becomes buoyant, and it's acted upon by the convection, which brings up these buoyant parts. It's buoyant because you're displacing gas pressure with magnetic pressure. So you end up with these magnetic loops, which are drawn in circles, but they're actually magnetic loops here. And then these loops, over time, get stretched out into another toroidal field going the other direction. This is the basic alpha omega dynamo mechanism. Does it work in the sun? Probably not. The sun is much more complex than this. But more or less, this is what happens. One of the big fields of study right now is how does the sun really work? There's a lot going on. It's not just spots migrating down to low latitude. There's also a lot of flux migrating upwards towards the poles, which causes the next cycle 11 years later, and we'll see that. So that's the very basic introduction to the sun and solar activity. So the next question is, what does this have to do with the Earth? We're talking about an object 93 million miles away. It's got magnetic field. What does it do to the Earth? Well, the main thing it does is it shines during the day, and we get a lot of energy from the sun, and here's the basic equation, which all you students should know, and if you don't, you should learn it. So the sun puts out one solar luminosity, that's 4 × 10⁻³ ergs per second. It's at a distance d away from the Earth, 1 astronomical unit, so this is the solar constant, L/4πd². A fraction of that is absorbed. It's πr². The r is the radius of the Earth, and it projects. The Earth projects a disk to the sun, not a sphere, but it looks like a disk. So it's intercepting πr² over 4πd² of the entire celestial sphere. A is the albedo of the Earth. It reflects 30%. A is about 0.3, so it absorbs about 70% of the light. And then the Earth is not just absorbing, it's radiating too. The Earth is in equilibrium. It's been about the same temperature for 4.5 billion years, so that's about as close as you can come to a good equilibrium. And it's radiating as a black body. The mean average temperature for the effective temperature of the Earth, T⁴, and 4πr², it's radiating into 4π steradians. It radiates as a sphere, not as a disk. So you equate those two, you plug in the numbers, and you find out that the temperature of the Earth is 257 Kelvin, which is pretty cold. The average temperature of the Earth is actually 282 or 285 or something like that Kelvin. And the difference is due to greenhouse gases. So greenhouse gases are good. They keep the Earth warm. So that's the Earth. If you are interested in extrasolar planets and finding planets suitable for life, the Earth is not in the habitable zone of the sun. We're too cold. So the habitable zone is a very complex idea because it depends not only on the insulation, but also depends on the atmosphere of the thing that's receiving the heat. So that makes it very fuzzy. Habitable zones go from fairly narrow to enormous if you have a huge latitude of ingredients to make your atmosphere out of. So the irradiance of the sun, the total solar radius, the TSI, is important because that's the energy input to the Earth. That's the input that drives Earth's weather and climate and all of those things. What does magnetic activity have to do with TSI? Well, if you look at the record, here is the measured solar irradiance as a function of time, since we've had spacecraft up there actively measuring how bright the sun is. And this is integrated over all wavelengths. This is the bolometric luminosity to the sun. And this is watts per square meter received at the Earth. It's 1366 watts per square meter, give or take a bit. And what you can see is the irradiance actually changes on an 11-year cycle. And it changes by plus or minus 1 watt per meter squared. The solar forcing is actually less than that because it's not all absorbed. by the Earth. The interesting thing is that when the sun is active, when the sun is full of spots, it's magnetically active, the sun is brighter. Spots are dark. How can the sun be brighter when you're covering the surface of the sun, half a percent of the surface of the sun, with dark spots? The answer is that you're taking away some light in the optical, but you're putting back an awful lot in the ultraviolet, because the magnetic activity heats the gas, the photosphere surrounding the dark spots. You have faculae which more than offset the light that is taken out of the photosphere. The noise here is actually not noise. That is, those are spot groups crossing the surface of the sun. And they do take away light, but over time, but on average, you add more light in the ultraviolet than you take away in the optical. So the solar irradiance peaks, decreases, peaks, decreases every 11 years. It's a small effect. There are longer term trends. I should say, I'm going to ignore these 11-year cycles because climatologists and other people have been looking for 11-year trends in the Earth's atmosphere and the Earth's climate for decades, if not longer. And there may be some having to do with the North Pacific Oscillation and things like that. I don't understand all of these things. But it's not clear what the drivers are. It's not clear what the physics is. It's not clear if they're coincidental or not. 11 years is a short period of time. There's a lot of hysteresis. Things average out. So I'm not worried about the 11-year cycle. I'm interested in the longer term trends. We know that sunspots existed from 1610 to 1650 because there are records. This is Hevelius's drawings of spots in the year 1611. But then we know they went away. So here's the monominimum again. This is spot number, and the record gets better here because there are more people observing. But you've got the monominimum. There's a region here called the Dalton minimum, the end of the Little Ice Age, when things were. It snowed in Boston in July of 18 something or other here. But there was a minimum of spots, and here's a running mean of spots. You see a minimum here and a minimum here. These are real. This decreased number of spots is real. Few spots were seen, few aurorae are seen here. Aurorae tend to go along with solar activity because when the sun is active, you have coronal mass ejections, you have solar energetic protons hitting the Earth's atmosphere. They get caught up in the Earth's magnetic field. They spiral down magnetic field lines, and they at the north and south poles, and they fluoresce atmospheric oxygen and nitrogen, and you get the aurorae. So that's a proxy for solar activity in spots. So the spot record is pretty good here. I think we can believe that. Proxies for the activity is the sunspots clearly. H and K fluxes from the chromosphere. We know they correlate extraordinarily well with sunspots over the last century when we've been observing them. Beryllium-10 and carbon-14 are generated by galactic cosmic rays. Galactic cosmic rays hit the Earth's atmosphere unless they're deflected by the sun's magnetic field. And when the sun is active, the heliospheric magnetic field puffs up and protects the Earth. So there's an 11-year modulation in the creation rate of beryllium-10 and carbon-14, which you can then go and see in ice cores. It's really painstaking work. I don't think I can do that. But people do it, and you see these 14-year periods. And the aurorae are another proxy. So here are a couple of the proxies. Here's the sunspot numbers that you saw before. This is the beryllium-10 concentration. And if you smooth it appropriately, you can line up this with the monominimum, this with the Dalton minimum, another minimum here. There's no sunspot record back here. You look at carbon-14, and you can create, people can create this kind of a record. So this is a carbon-14 deficit or something. So here's the monomer minimum. There's a spore minimum in here, the Wolf minimum, the Oort minimum. So these are all supposed to be times when the solar activity decreased. And then the game the climatologists play is you try to correlate this with the temperature on the Earth and see if they line up. And more or less they do. So it looks like there are correlations between solar magnetic activity and temperatures on the Earth. This is the best one. It's the most recent one. We have real records for the Little Ice Age, went about 1350 to 1850. And during this time, you have the sporometer and Dalton minima. So the sun was doing something interesting, and the Earth's temperature may have gone down, or at least the temperature in Northern Europe may have gone down. It's one event. Is it a coincidence? Is it real? Nobody knows. People have argued in both directions. So we're going to have to look into the future and extrapolate what the sun is going to do. Try to figure, and that's hard. So here's the sunspot, current sunspot prediction as of March, as of 2 months ago. So here's the cycle 22 sunspots. The model is the line going up the middle as a minimum and maximum uncertainty that comes out of this model. Cycle 23 peaked about 11 years ago and somewhat lower, but these are sort of normal. Well, this is normal. This is a little bit low, but not exceedingly low. So you've got this empirical model that is constantly being adjusted. And it matches what's happening here in cycle 24, which is peaking about now. And it'll come down again. You see cycle 24 is peaking at about 70, and this one peaked at 3 times higher, and we're about half of where we were last cycle. So these 3 cycles are decreasing in intensity. And we've seen things like this before. There are cycles that are less active, that have fewer spots. There's a difference with this one. For one thing, we have more data. That means we can worry more about things that may or may not be important. But we have more data, and we can try to extrapolate what's going to happen in cycle 25 and cycle 26. So here's some of the data that we have that we never used to have. You can look at the magnetic field strength in the sunspots. This is data from the National Solar Observatory, Bill Livingston and his group. And the magnetic field strength that they measure has been decreasing linearly with time over the last cycle and a half or so, from about 1998 to 2012. This is controversial. There are groups that have tried to reproduce this and have failed to reproduce it. On the other hand, it looks very interesting. If this continues, you hit in about the year 2022 that dashed line, says no spots. Once the field drops below about 1500 Gauss, you do not expect to see sunspots on the surface of the sun. The spots will, the magnetic flux tubes will not get pushed together to form spots. So we could be approaching a time when there are no spots on the sun.
Frank,
Yeah.
this is normalized to the number of spots?
This is,
normalization?
no.
No.
This is the average magnetic field strength in a spot. I guess it's average over all the spots that they look at.
Okay.
So this is a measure in Gauss of the field strength emanating from the sun. And that's been apparently going down with time. Okay, there's another less ambiguous measurement. What is the polar field strength? The sun is more or less dipolar in the far field approximation, and you can look at what the polar, and you see they reverse here, but the strength at the previous cycle at minimum was 7 or so Gauss, the polar strength. Now it's down to 3 or so. So it looks like the polar field strength has weakened with time. I don't think this is controversial. The interpretation may be, but the measurement I don't think is controversial. It's a very complicated slide. This shows that something interesting is happening in the interior of the sun. This is from helioseismology. We can measure the rotation of the sun. In this case, it's how is the sun rotating 7,000 kilometers below the surface? And if you subtract off the mean differential rotation, the mean rotation rate as a function of latitude over the last 30 years or so, 20 years, you end up with this plot. This is in meters per second. This is a meridional flow, subsurface, 7,000 kilometers down. And there are these, this branching pattern, this V-shaped pattern, is basically the sunspots. This is following the sunspots as they approach the equator during the solar cycle. And here's cycle 23 and cycle 24 that we're in the middle of now, and they look more or less the same. I don't know what scaling has to do with how you scale this or how you interpret it properly, but this is the signature of the sunspots 7,000 kilometers down where the magnetic field is rooted. Actually, it's probably rooted even further down, but down at this velocity, or at this depth, the gas pressure is high, and the gas is actually dragging the magnetic field. So that's not true at the surface, but it is as you go down, the gas pressure dominates. But what happened previous cycles, it probably happened in earlier cycles, but the data aren't as good, is that you have this poleward branch too. This is the equatorial branch of this meridional flow. Then you have this poleward branch that appears about 11, that's associated with the next equatorial branch. It starts at high latitude and it moves up towards the poles. This is associated with the magnetic field of the sun migrating towards the poles. The quiescent field, the field that's not in the active regions, migrates towards the poles. This has been known for a long period, for a long time, 30 years or so. So, and this happens, this starts before this cycle. It's all part of the same cycle, but it starts going north before you approach the equator. Well, so it shows up here for cycle 20, well, here's the end of the cycle 23 poleward branch, here's the equatorial branch, here's cycle 24 poleward equatorial. Where's the cycle 25 poleward branch? It should have started here, and it's not there. So something unusual, since we've only seen 3, it's hard to know how unusual it is, but something unusual is happening in the interior of the sun. Now, it turns out that if you allow for the differential rotation of the sun having changed over time, so the differential rotation law changes again, we don't know how or why this would happen, then you can actually see a small, well, this thing here, this small increase. This is what happened last cycle. This is what's happening this cycle. If you allow that the differential rotation rate of the sun has changed with time. Why should that happen? Nobody knows what's going on here except the sun seems to be changing in front of our eyes. Unfortunately, it's changing not fast enough for some of us. We're impatient. We want to see what's going to happen next. But the sun is changing. So you put together the fact that the magnetic field overall seems to be changing with the fact that the meridional flows subsurface are changing, and maybe something wonderful is happening, but we don't know. So at this point, I have to remind you that when we start making predictions, we're really getting out on a limb. But there are, fortunately, solar physicists who like to make predictions. So here are predictions. These are predictions of sunspot number, two different models. Well, this is the radio flux, this is the sunspot number, and the model is the blue line coming through here, I believe, and the red is the prediction, and they're sort of matching. Actually, sunspot numbers are coming down below the prediction. So here's on a different scale what these predictions are. It's a semi-empirical model because it has to fit the past data, so this is coming down, and the question is what happens next. So this guy, Abdusamadov, has done some modeling. He goes much more out on a limb than the National Solar Observatory is willing to do, and he goes out to the year 2050 or so, and he predicts that the sunspot numbers are going to go down to 0, that this total solar radiance is going to drop from 1366 to 1360. That's 6 watts per meter squared. The total fluctuation now is plus or minus 1, so that's a huge drop. This is his prediction of solar radiance. This is our current cycle. This is the next one. The next one gets even smaller. Solar activity coming down, and he gets a drop in the total solar radiance. Where does this drop come from? It comes from the fact that in his model, as the solar magnetic activity weakens, as the field weakens, the faculae weaken too, and the faculae are giving you all that ultraviolet light that would normally be coming out. The optical light doesn't change much, but this is all ultraviolet light. So here are some of the predicted changes that the sun solar luminosity could drop by 0.5%. Or it might not, but in this model it could. Does 0.5% in the sun affect the temperature of the Earth? A couple of degrees. It's not significant. It's not significant compared to what we've been doing to our own atmosphere. But a couple of degrees could be significant. What's important, though, this is what a lot of people forget, is that it's not about the total solar irradiation, it's the fact that the spectral energy distribution changes. By the way, Carl Schreiber doesn't agree with this. He says it's not going to go down at all, or maybe a couple of watts. So this is the solar spectral energy distribution. It's this blue, the spectral irradiance, this blue line, function of wavelength from the X-rays up to the radio. And it's more or less a black body up to about here, and then we have absorption due to iron in the Earth's atmosphere, in the terrestrial, in the solar atmosphere, causing deviations from the black body here. And there's some flux, but not very much flux. This is a log plot in the ultraviolet and in the X-rays. What happens as the sun varies, as the sun goes through a cycle, a normal magnetic cycle, is that it doesn't vary much here. This is the spectral variability, and this is a lousy color, but this is a log scale here. So here's 1%, here's 100%, 1%, 0.01%. So the variability here in the optical, where most of the solar flux is coming out, is negligible over a solar cycle. But in the ultraviolet, you're varying by 100% or more. The sun varies in the ultraviolet, in the UV, in the X-rays, and in the radio. There was a demonstration that was given by a solar astronomer that's had a great effect on me. This is back in the 1970s, and I still remember it. Is that he said, this is how the sun varies. Here's the solar spectrum. When the sun varies, it goes like this. The extremes go up and down. They don't contribute a lot to the total, but the extremes go up and down. And the extremes can be important. And I'll get into that. So, just to remind you, this is the correlation of the total solar radiance with sunspot number. The sun is brighter when there's more spots. And the question is, if the spots go away, what happens? To remind you, this is what the sunspot numbers look like. So here's a reconstruction of the total solar radiance based on sunspot numbers. This comes from this instrument on some satellite. It comes out of the University of Colorado, and this is where we are now. The absolute numbers, there are scaling factors between instruments. So is this 1361 or 1366? You pick one, you pick the other, you scale everything else to the one you like best. So their model of the total solar radiance is it goes from about 1361 or so now to 1360 and a half in the quantum minimum. That's a negligible change. However, it's not just the total solar radiance. There are other effects, which I don't completely understand. I read the literature, and some things sink in. The heliospheric magnetic field weakens when the sun magnetic activity goes down, lets in more galactic cosmic rays, you generate more nitrogen oxides or nitrous oxides in the Earth's atmosphere that destroys ozone, reduces stratospheric heating, and may affect global circulation. I can refer you to papers that say this. And then there's this prediction that the theta psi may change up to 6 watts per meter squared, and not just 1 watt per meter squared when the activity goes away. This all depends on what happens to what are called the ephemeral regions. The ephemeral regions are the regions in the quiet sun where the magnetic field does not concentrate enough to give you a spot, but there's enough there to heat the chromosphere. It's basically the edges of the granules where the magnetic field is pushed to the edge of the granule, and it concentrates a little bit, enough to heat the network. The question is, does the network go away at a grand minimum, or does it stay? And we don't know the answer to that. The answer is either yes or no. One interesting question that comes up is, if the sun is cooling off, if the solar activity is going to make the Earth cool off like it did in the Little Ice Age, if it did, does that affect anthropogenic warming? The naysayers look at this and say the warming has stopped, the CO2 is still going up. And there's an interesting paper by Rozanov et al. That say that solar forcing at the extremes can offset maybe 50% of the anthropogenic warming, which may save us in the next 50 years, but we better watch out when the sun turns on again. So I'm not going to touch that. Okay, so let's put the sun in context. I'm a stellar astronomer. The sun is one star. We have one example of what the sun does. And we've been watching it for 400 years, and is the monominimum something significant? Does the sun really change on timescales of centuries? Let's look at other stars. There are lots of stars out there in the galaxy like the sun. There's 100 billion stars in the galaxy, and there are certainly hundreds of millions that are more or less like the sun. In the 1970s, Vaughan and Preston at Mount Wilson Observatory started a program of monitoring the calcium H and K line fluxes in a series of solar-like stars. They wanted to put the sun in context. So here are 6 stars. The sun is here. This shows what the sun looks like on the scale. And you see the 11-year cycle in the calcium H and K activity. Here's a star, somewhat more massive than the sun, a little bit of cyclic behavior. This shows a nice cycle. This shows a shorter cycle. These are just samples of the kinds of data you can get. In context, here's a whole bunch of stars. The sun is right here. This is a measure of the chromospheric activity. The blue points, which are hard to see because they look like black points, at least to me, the blue points are stars that do not have cyclic behavior. The red ones have cyclic behavior. The sun has cyclic behavior. It's an 11-year cycle. The black ones haven't been measured. But the sun's activity is sort of in the middle here. It's halfway between the generally inactive, flat stars and the ones that are more active and have cycles. So the sun looks like an average star, which is good. Here's more data. This is part of the Donahue and Baliunas follow-up to that Vaughan Preston survey. Lots of stars. The sun is over here. Some are flat, some are cyclic. There's a few more. Put it into context. Here's again the measure of the brightness of the calcium H and K lines, temperature of the star. The sun has a color, E minus V color of 0.62. Here's the sun. There, I won't talk about the dashed line. The C's are cyclic stars, V are just highly variable, and the F are the flat stars. The sun seems to be borderline between the stars that, but it's certainly it's on the low to middle side of the activity levels for solar-like stars, and it seems to be borderline between the stars that are flat and inactive and the ones that are much more active and cyclic. So here's a star. There are a couple of stars like this that was observed for 25 years. It seems to be cyclic, and then the cycle seems to have stopped. The average flux seems to be going down. It'd be nice to know what happened between 1992 and now. Funding was cut for the project. These things happen. But the question is a star like this turning off? Is a star like this entering a grand minimum, a Maunder minimum type of phase where its activity level is low and it's not doing the cyclic behavior? Well, you can look at a lot of stars. You can do the statistics and say, what are these? How many stars like the sun are in grand minimum? Of course, first thing you have to do is define what do you mean by a solar-like star. Throw away the binaries, throw away the very young stars, throw away the subgiants, the more evolved stars, limit the range in effective temperatures. Turns out that's an important thing to do because cooler stars are more convective, hotter stars are less convective, and this seems to have play a role in things. And the estimates range in the literature. At any one time, a solar-like star, the probability that we'll be in a grand minimum, where it's inactive, magnetically inactive, is between 3 and 30%. Huge range. The two best studies, Marchi and Papa looked at the cluster M67, which is 4 billion years old, and there's about 60 stars, more or less like the sun, in it that he studied, and 17% of them are inactive. They're less active than the sun, and over for 6 years anyways, don't seem to show cycles. Starr and Tesla did more of a review, and again came up with the 17% estimate for solar-like stars in the grand minimum. So if the sun is, if these estimates are correct, and the sun is a normal solar-like star, then you would expect 10 to 20% of the time, it would be in a state of magnetic inactivity, something like the Maunder minimum. Well, we've had 70 years of Maunder minimum out of the last 400, so that's perfect. Okay, so conclusions. The question is, and I'm not answering this question, the question is there a connection between the Maunder minimum and the little ice age? And there are 3 possible answers. It could be a coincidence. This has been 1, it's the statistics of 1 still. Could it be due to a low total solar radiance? We don't know what the total solar radiance was there, and there are 2 models, and they give you very different answers. Or could it be due to other effects? Because we know that the solar spectral energy distribution changed. And could it be due to the fact that all of a sudden you do decrease the ultraviolet flux by a factor of 10 or more? What effect does that have on the stratosphere? I'm not an atmospheric guy. I don't know the answer to that, though I know people are worried about this. So here are some of the conclusions you should walk away with. The solar magnetic activity does vary. It does vary on time scales of centuries. Right now, solar magnetic activity seems to be weakening. Certainly something is changing in the sun. The differential rotation may be changing, and the magnetic fields seem to be weakening. Something like 10 to 20% of solar-like stars seem to be in a state that we think characterizes a Maunder minimum with low activity, non-cyclic, or flat activity behavior. They are not variable, highly variable stars. And if you put this together with this, it's not unreasonable to say that the sun may now be approaching another grand minimum, much like the Maunder minimum. And the big question, which I am again not answering, the question is, what is the effect of a prolonged decrease in solar activity on the terrestrial climate? And I throw this into your lap because you're the guys who model climate. This is the input. I'll tell you what the input is, run with it. I think this is important. Or we can just wait 11 years and see what happens with the next cycle and see what happens with the Earth's climate. Thank you.
Great, thank you.
And 2 good references if you compendia if you are interested.
Fred, what is the orientation of the axis of rotation of the sun with respect to, what do you call it, the ecliptic, the plane of the Earth?
It's 7 degrees.
7?
It's inclined by 7 degrees.
So it's almost perpendicular to...
Almost perpendicular.
Why is that? I mean...
The angular momentum of the cloud that the solar system formed out of.
So what would happen if it were like that and the Earth was going around? You wouldn't see sunspots anymore, would you?
Yeah, you would see sunspots.
They're around the equator, you said, more or less. So if the Earth's going like this...
Passed by the equator twice a year.
Oh, well, if you're orbiting perpendicularly, you'd see the equator, you see the pole, and the equator again. The solar system is defined by the sun and Jupiter. That's all that really matters. And so the Earth's orbit is inclined a little bit. We do not know, there's a lot we don't know about the heliosphere outside of the equatorial region. We have sent some spacecraft up, but you know, a lot of our extrapolations depend on our vantage point. But we think we know pretty much what the sun does.
And what's the rotational period of the sun?
27 days
27
on average.
days?
It varies from 25 to 30 depending on the latitude.
Kamaluma?
So could this weakening have something to do with the convection, that maybe the light state turbulence is decreasing? I'm trying to think, what is it changing the coupling between the different layers?
Nobody knows. I don't know. The time scale for changes in the convection should be much, much longer. We're talking about convective velocities of a kilometer per second, and the size of the convection zone is 200,000 kilometers. So the time scale for changing these things is fairly long. Well, actually, that's not the way to do the time scale. The time scales, it comes out short. But the time scales, the convection of the sun is independent of the magnetic field. This is set by atomic physics. So it's radiative transport through the gas.
Yes.
Can you be more certain about the forecasting the spectrum and changes in the infrared than you can be about changing the overall irradiance? Or is the change in the spectrum contingent on your forecast for the overall irradiance?
Yes and no. We know how the spectral energy distribution changes with magnetic activity during a normal cycle. What Peter Foucault argues that if you go into a grand minimum, the activity level drops to a point where even the ephemeral regions disappear and the UV flux goes even lower than it does in the quiescent sun. And this is what this Russian guy picked up on when he's predicting that the TSI drops by 6 watts per square meter. Karl Schreiber and his group, based on the last 3 cycles, claim that there is a minimum activity level that has nothing to do with the magnetic cycle. And the 2008-2009 minimum was the weakest we've seen the sun, at least in the last 3 cycles, and the flux level in the ephemeral regions in the quiescent sun was the same as it was in the 2 cycles earlier in the quiet regions. So they claim that this is a base level that has nothing to do with the magnetic field, with the cyclic magnetic field. Therefore, if you lose the cyclic part of the field, you go into a Monte minimum, you don't lose any more flux. So these are the 2 extremes. We will know in 11 years. But right now we don't. Or maybe 22.
Edmond?
I'm just wondering, there are people doing sort of physical modeling of stars. So what's the progress in those areas? So I guess we are still far from being able to run a model of the stars to try to really understand how to predict how it changes.
What level of accuracy do you require?
Well,
We
the
have-
accuracy that we see any change.
We have exquisite models of the sun. We have helioseismology data that tells us everything we want to know about the run of temperature and pressure with radius in the sun, at least down to the tactile. We can predict the nuclear fusion. We see the neutrinos coming out, and we can match the sun perfectly. Except we can match the gas physics, but we cannot predict the dynamo. We do not understand what drives the solar dynamo. And there are a number of models out there. So on the level of a star, a non-magnetic star, I think we understand them fairly well. You throw the magnetic field in, you're talking about a perturbation. And we don't understand that small perturbation, but it's an important one to try to understand. We are getting, we have to make sure that we continue to monitor the sun in the ultraviolet, that we have spacecraft doing TSI measurements. We're getting a new solar observatory, the Daniel K. Inouye Solar Telescope, DKIST. It'll be up and running. It's being built now on Haleakala, Maui, Hawaii. That'll be operating in 2020 or so, 2019. They'll have some fantastic instruments, even more data that we don't completely understand. Solar physics, if you students out there want something challenging to do, look at solar physics. We have we have exquisite data Unfortunately, it's plasma physics, it's got magnetic fields in it, and it's very complicated. But it's important to try to understand.
So for the prediction of the solar cycle 25, you said that the model was somewhat empirical. Is it based on electromagnetic hydrodynamics, or it's purely empirical model?
There's a little bit of physics, but it's mostly empirical, actually. And the models are that cycle 25 should be weaker than cycle 24.
As oceanographers, we marvel that the Earth has so much liquid water on it, covering 71% of the Earth's surface. And the question is, where did all that water come from? Now, all I know is, it maybe came in comets, but why water? I mean, what would happen if the comets were solid carbon dioxide? Then we would have an uninhabitable planet, wouldn't we? So where does all this water come from?
There's a lot more water in the universe than carbon dioxide.
Well, I just picked carbon dioxide as yeah, I'm not picking on CO2 in particular, but...
Yeah. The theory, I believe that the theory that the water came in on comets has been partially debunked because the various isotopic ratios, I think it's the D to H ratio in the hydrogen, is not consistent with cosmic origin. I think a lot of it is outgassing. It's just from the rocks that the hydrated minerals that the Earth formed out of. There was a lot of water in the early solar system. But I'm no expert on that either.
Okay, so let's thank Fred again. We have lunch in the Akuba room. You are welcome. I have joined.